Okay, so I'm going to continue where I left off, which was the tough last question of 2.1, and then I'm going to move on to 2.2, which is derivatives of polynomials, which is really what we've been leading up to. Turns out this one was pretty complicated, and I was just missing one crucial step. So I've outlined the steps here, and if you want to do it. So first out, you figure out the derivative of the function using your x plus h squared minus x squared, and you end up being left with 2xh plus h squared. And then when you factor an h out, you're left with 2x plus h, and then when h reaches 0, you're left with that. So you're going to discover that the derivative for this function is 2x, and that this will produce any slope of a tangent based on the x you choose. So the second thing that you realize is that when you draw this tangent, that the point in question is somewhere here, and it will make two separate tangents, both with a spot over here and with a spot up here somewhere. And that these x values, let's call it xy here and xy there, it doesn't matter if I make them different, are very different spots on the parabola. Okay? That's not so much a problem, but this dot over here, as you will remember, is given as that point. Well, next, you then assign a mysterious unknown xy value, which I've done, and then you do a slope calculation from here to here. Forget about that for now, it'll produce itself. And so what you end up with is this mysterious y point here, minus 3, over x minus 1, which is essentially just delta y over delta x. And this is going to be equal to the slope of this line, this tangent line. But we also have determined that that slope formula is 2x. Okay? But you also, and here's this part I was missing, I was failing to solve for y. But I also realized that there is a replacement for y. And that's right up here. Y is equal to x squared, which means I can replace my y with x squared. And once you have that, you're able to solve it. So let's look at that solution there. Go ahead and pause videos whenever you need to write things down, by the way. Okay, so this is finally what we have. We have x squared minus 3 up top, which becomes x squared plus 3. X minus 1 is equal to 2x. How do you get rid of something at the denominator that just treat it as one big number? You multiply it by its reciprocal. So there's its reciprocal, but if I multiply on the left side by its reciprocal, I must multiply on the right side. And these cancel out. So I essentially get rid of my denominator. When I expand this over here, I get 2x squared minus 2x. Okay. And if I move everything from the right side over, I get minus x squared, so minus x squared, which means this x squared just becomes 1x squared, and I get minus 3 equals to a 0. When I factor this, I discover that I have x minus 3, x plus 1. Great. Right there, I've discovered my two x values for here and for here. Because for this to be equal to 0, x would have to be equal to 3, or x would have to be equal to minus 1. Now that I have my 2 points, I have to forget all of this and go back to my equation, which is f of x is equal to x squared. And I plug in my 3 here to produce the point 3, 9, I plug in my minus 1 here to produce the point minus 1, comma 1. Great. Now I have my 2 points. Pretty long, I know. And now that you have your 2 points, you can do, and you also know the slope of this one is 2x, which is equal to minus 2. And you know the slope of this one is 2x, which is equal to 6. So the 6 is equal to the m on this one, and minus 2 is equal to the m on this one. And now that you have a slope and 2 points, you can use the equation for the line graph to figure it out. Go back to my other questions if you don't know how to do that. But essentially you sub in this for here, and minus 2 for here, and now you can solve for b. And then you do it again for the other line. Complicated, but not too bad. Section 2.2 is all about derivatives of the polynomial, and that's why we did independent limits. That's why we did it. And you're going to discover that the derivative of a constant just comes out as 0. So whenever you see a number in a polynomial, it's going to just derive out to 0. And that's done when you take a slope of a flat line like this. You realize the slope of a flat line is 0. And this is y is equal to minus 4. And then you discover that you can also prove it like this, where k replaces this. And you discover that it becomes k minus k, which becomes 0 up top. And then they also go through the power rule, and the power rule is incredibly useful. And they go ahead and demonstrate up above. But the power rule, as you probably know, simply means and notice how their rule summaries are really confusing. So I want you to look at their rule summary. And keep in mind this is for the derivative. And they're saying for this function. So I'm going to give an example instead. So let's say this function is x to the cube. The power rule says that you take this n, you see this n, and you put it in front. This is to figure out the derivative. So the derivative is going to be equal. So you take that 3, you put it out front, you keep the x. And what does this n minus 1 mean? It means you take the exponent that was there and you lower it by 1, which means that the derivative of x cubed is 3x squared. And you're going to discover this is true for any of them. So what do I do here to find if this is f of x? The f prime of x, which is how you say derivative, is going to be 5x4. So I brought the 5 down, and I lowered it by 1. You're going to discover any value of x, this will give you the slope of that equation for that value of x that you plug in. Very useful. Now, I'm going to go through the other rules that they're going to give you, but they've also discovered that when there's a 3 in front of it, let's say, so the rule becomes you can just leave that 3 there. You can still bring the 4 down, and then you just lower this 4 down to 3, and then you just multiply out whatever constant was in there. So this is the derivative for the function for x cubed. So now you can find any tangent of any slope of the tangent for any value of x for this function using this formula. Very useful to just be able to do this and not go through the x plus h minus x. And when you want to prove it, just do it generically for any formula like this one using this method, and you'll discover you come to the same conclusions and you'll see a pattern. Okay, that's great to know. So it's called the power rule. And guess what? The power rule also works for something like this. Okay. Because this is the version, the exponent version of that. What do I do? I bring it down in front. So if this is f of x, f prime of x, the derivative. I bring it down in front. And you might say, well, how do I subtract 1 off of a half? Well, 1 half minus 2 1s becomes negative 1 half. This is the, 2 over 2 becomes, this is what 1 is, becomes negative a half. And you can see 1 minus 2 minus 1 over the same denominator. So you might say, okay, that's fine, but what the heck is negative a half? Well, whenever you have an exponent, go visit your exponent rules, that is negative. All the negative means is, if it's in the numerator, put it in the denominator. So x to the minus half is the same as 1 over x to the positive a half. So you can see that this is all this minus means. It means send this, if it's at the numerator, send the whole thing to the denominator. And what does that mean? It means 1 over square root of x, which means I can replace this whole thing with that, and that ends up being 1 over 2 times square root of x. This is the formula for the derivative, which gives you the slope of any tangent line for any x for this function. Okay? And you might say, wow, the tangent slope formula is more complicated than the original formula. Yeah, but at least you can use the power rule to figure it out. You don't have to go through the x plus h anymore. And you're going to discover that there's special circumstances for more complicated exponents. You can't do this yet. You can only do the simple ones, like 2x cubed. This becomes 6x squared is the derivative. I brought the 3 down, multiplied by the 2, and I lowered the exponent by 1. And that's what n minus 1 means and n means. It means take the exponent, put it down in front, lower the exponent by 1. Great. And then they give you always a bunch of examples. And they let you do it the long way, and then they let you do it the short way. Okay, and the constant rule is what I just explained. The constant, when there's a number, a coefficient in front of your term, you can just take the derivative of the term and then later multiply it by the constant. Okay. And they do it here. So what is 7x cubed going to be? You're going to bring the 3 down in front, times 7 is 21, and it's going to be x squared. So it's going to be 21 x squared. What about this one? Let's do that one. Because you might say, you didn't cover that one. Okay. We'll keep the solution too. Hopefully you can see it. So we're talking about 12 to the 4 3. So the derivative, we bring the 4 3 in front. We get 4 thirds times 12. Let's figure that out first. 3 goes into 12 4 times, so it's 4 times 4, 16. So that's all that happens to the coefficient. It becomes 16. And by the way, it was x to the 4 thirds. Now, let's do the x to the 4 thirds separately. I said you take the exponent and you subtract 1. Well, what is 1 over 3? It's 3 over 3. And now we can just keep the denominator the same. And what's 4 minus 3? It's a third. So x to the third is the final answer, 16x to the third. And that's what they give. And you might say, well, what is x to the third? X to the third is the same as this, 16 times the cube root of x. That's what that 3 means. The bottom of a denominator of an exponent means the root. The top means the power, 1. And if it was negative, it would mean put the whole thing at the bottom. Okay? So if we'd had a negative a third, it would mean this. Okay? Exponents are easy because once you learn the rule, it's the same rule over and over again. Okay? And just to make it clear what this means, x to the 4 thirds, it means cube root of x to the power of 4. That's what it means. The power is here, the third is a root. And you can write it two different ways, actually. We can write it like that, to the 4. But this is a little bit messy, because it looks like the 4 doesn't belong to the x. Okay. And again, the book always has excellent rules. Now this just says that when you have a polynomial, you can take the differential of the terms separately. Okay. So if I have f of x is equal to 3x squared plus 5x plus 7, which we've seen stuff like this a lot, you can just do them separately and just keep the plus signs. So we're going to keep the plus signs. And this plus sign might disappear. You'll see why. So we'll do this separately. We take the exponent down. Becomes 2 times 3. We reduce this exponent by 1. So it just becomes x to the 1, or x. 2 times 3 is 6x. Which means the derivative of this function, f prime of x, is equal to 6x. Now what about this one? 5x. Okay? That x has an invisible 1 over it. So the 1 comes down, multiplies down to the 5, and gets reduced to 0. What is x to the 0? Just 1. What is 5 times 1? 5. So you can see that x values here become constants in the derivative. And you can see that squares become single powers in the derivative. What about a 7? Well, we learned that the derivative of a flat line, like y is equal to 7, is 0. So the derivative of 7 is equal to 0, which means we have plus 0. Well, there's no reason to write plus 0. So just remember that numbers will disappear. The plus sign doesn't matter with numbers. So you end up with this. That's the derivative. It's nice because you can break apart, no matter how long this polynomial is, whatever I have in it. You can break it down into individuals and then just keep the plus signs preserved in the, or whatever sign is preserved in the equation. So that's another good rule. That's called the sum rule. And then the difference rule is the same thing, except when they're subtracting. So it doesn't matter what the sign is in between it. Then they give you some good examples. All right? The summary at the end of the chapters is always a fantastic thing to look at if you don't want to read the chapter. I strongly urge that if you take science seriously and math seriously, that you read the textbooks. Because sometimes the textbooks are better and clearer than the instructions in class. So there's the constant rule, there's the power rule, there's the constant multiple rule or constant power rule, there's the sum rule. And notice that their summary of these things is pretty damn confusing. That's why the examples are better. Oh, there's a good example. What if I had 4 over x to the 3? Okay, that's the same as 4 times, and how do I bring this x up to the numerator? It's the same thing, I just reverse it. It's minus 3. X to the power of minus 3 is the same as 1 over x to the 3. Great, now I just follow the power rule. I bring this number down in front. It's minus 3 times 4. That's minus 12. I reduce this. I subtract this by 1, which becomes minus 4. So I got minus 12 times x to the negative 4. What is x to the negative 4? It's the same as 1 over x to the 4. And so now I end up with 12 times 1 over x to the 4, which is simply minus 12 over x to the 4. And now we have a tangent equation for what looked like a complicated rational function. Now keep in mind, these rules will work great for these situations. So I can still apply the same rule, but will not work for these situations. Hang on. Boom. This requires a whole different thing, because it's really the expansion of that. If you were just to solve these individuals, you'd end up with this. And then you'd say, well, now I'm going to cube it. Well, it doesn't work like that. You'd have to expand this entire polynomial, and then you end up with a thing that has 6 terms, and then you have to individually do the derivatives. Well, that takes a long time. So there's going to be a rule coming up next chapter about how to solve these. So this, yes, you can solve with the power rule. They all come up top, and it ends up being 4 times all of that. Oh, and actually, you know what? You can't solve this with this 4 in this power rule because it all ends up being in a bracket plus 7 to the minus 1. And this requires a separate rule. So you cannot solve something that's a long polynomial in the rational. We'll get to that in the next chapter about what you do for those. Okay? But the single ones, when it's just a single one, yes, you can solve. So the rules I've just given you will work fine for simple ones, and they're going to get you to practice. Okay, and the simple questions here, I'm only going to walk through certain parts. Okay. And then this just goes through the rules, so you can just go through them again. Okay, what's the rule? This is 4x. We just do them separately. Okay, so that's 4x to the 1. Bring the 1 up front, lower it by 1, so it becomes 4. So it becomes 1 in front. 1 times 4 is 4. X to the 0. X to the 0 is 1. So we get 4. What about the number? That's just a number. It's going to be constants. Derivatives of constants are 0. So the answer to this is, what is the derivative of this one? It's that. Notice how simple it is when x is just... Now this makes sense, because look at this formula. What function is here? What is this? It's a line. And lines have a constant slope. It's the same slope for the line no matter where I take it, which means no matter what x value derivative I take for this slope, I'm always going to get an answer of 4, which makes a lot of sense because a line slope is a constant. Okay, what about this one? Same rule, and it's a lot easier if you separate them. Okay, you take the x3 here, keep the minus, and actually assign the minus to this value here. Makes it a lot easier because it's like having a minus 1 in front. So x third becomes this. What did I do? I brought the 3 down. I lowered the exponent by 1. And then this 2 comes in front and multiplies the minus 1. Becomes minus 2. And then when I lower this exponent by 1, I get x to the 1 or just x. So that means the derivative of this equation is 3x squared minus 2x. Notice the pattern. You can see both of the derivatives in this equation. And you can't simplify it because this is an x squared, that's an apple, and that's a banana. You could subtract them if that was an x squared, but not if it's an x or an x cubed. So this is as simple as it gets. What about the next one? Okay, break them down into their individual components and keep the plus symbols with the number in question. It'll make it easier. So this 2 comes down and multiplies this minus 1, so I get minus 2x because the exponent goes down to 1. This plus is always easier when it's x to the 1. It just becomes the number. And numbers disappear. So I'm left with minus 2x plus 5. Minus 2x plus 5 is the derivative of this function. It's easy to see in there once you get used to it. Okay, so they're giving you more complicated ones. Please note that at this stage, we can do roots in their simple format. But if this said x plus 3 in there, or let's say x squared plus 3x, we would not be able to do it. Okay, so we can do roots in their simple format. If it says 3x, we can do it. So what is this equivalent to? X to a third. Let's bring the third down. And we're going to subtract 1 off this, and I get negative 2/3. Okay, what is x to the negative 2/3? It's the same as 1 over x, and this is the part you have trouble with. So go over this over and over again until you get it. And what is x to the 2/3? It's the same as 1 over the cube root. I got that from here, of x squared. I got that from here. So when I multiply this 1/3 over it times it. The 1 multiplies the top, and the 3 multiplies the bottom. So that's it there. A little bit more complicated here, but it follows the same rules. And you might say, how did the 1/3 get at the bottom? Well, it's 1/3 times the thing we figured out. So you just bring the 3 beside it, and this just becomes a 1. Fractions are easy to multiply. It's numerator times the denominator. Great. What about this one? Same rule. Doesn't matter. In this case, it's very important to notice that the 2 is inside there, because our first step for figuring out the derivative, bring the 4 down, okay, make it a coefficient, and reduce this 4 by 3. And that's it. You can just stop there. That's all it is. Sure, you could expand this, but why? They just want to know what the derivative. It's actually easier to solve it like this, because when I'm solving for like x is equal to 2, I can just put the 2 in there, realize this is 1. 1 to the 3rd is 1, times 4 is 4. So when x is 2 here, the derivative is, the slope of the tangent is 4. A lot easier to solve without expanding it. When you do come up with a derivative formula, you're going to discover that simplifying it isn't always the best method, even though the book will give you lots of examples of simplifying it. This one follows the same rule. The minus 3 comes down in front, and then what is minus 3 minus 1? Minus 4. And you can just leave it like this, or you can also write it the way I like to write it. So x to the minus 4 is the same as 1 over x to the minus 4, and it's all times minus 3. So that would be also a final answer. Okay. Says using either method, Leibowitz or. Okay, this is a good point. Later on, we're going to learn a method called the product rule that will let us solve this without expanding. But right now, just like in other sections of the book, the only way to solve this, because you might say, well, I'll find the derivative of this and derivative of this and multiply it. Well, we didn't do a product rule. We only did a sum and a negative called a difference rule, and we did a power rule. You cannot solve this by just taking the derivative inside. Later on, there's going to be something called the product rule, but right now we must expand it, and we get 2x squared plus 8x plus 3x, and you notice the middle terms can add, plus 12. So the middle terms add, and you get plus 11x plus 12. Well, right away, I can tell you the derivative of this is just going to be plus 11, because when you have x to the 1, it's very nice. It just becomes a number. It becomes a constant in the derivative. This one, the 2 goes in front, so I get 4, because 2 times 2. X, this is reduced by 1, so it's just x to the 1. And plus this is always ends up being plus 0. A number, a constant, the derivative is always 0. So you can see how nice and easy the derivative was. 4x plus 11 will give me any slope of the tangent for this function. Just be aware of what you're calculating and what you're coming up with. You might say, this one I'm just going to do fast, and I'm using the same thing, and you see if you can follow. Done. So here I brought the number down, multiplied the 2, 6, lowered the exponent by 1. Number down, multiplied the 5, lowered the exponent by 1. Number down, 1, brought the exponent down by 1. X to the 0 becomes 1. X to the 0 does not become 0. It becomes 1. So that's why x's are easy to solve. Any number to the 0 is equal to 1, to the power of 0. And then, of course, this number is just 0, so I don't even have to worry about numbers. So that's it, pretty fast. So obviously they're going to give you complicated ones. Now, later on, you're going to discover that you can solve these with a product rule, but right now you must expand it. So what's the derivative of that? You should be used to it now. I'm not going to walk you through it. I will for the tougher ones. So we've done all that. Put this one over here. What about this one? Well, just remember that those things in front of it are just numbers. They're just constants in front of it, coefficients. So you still follow the rule in that you treat each thing individually, and that will be the best way you can go about it. Now I'm going to forget about the number because I know the difference of a number is just the number. 5 goes in front, so I get 5 over 1 times 1 over 5 becomes 1. So this just becomes x to the 4 because I got to lower the exponent by 1. This one, the 3 goes in front. I get 3 over 1 times 1 over 3. It just becomes 1. So they're just getting tricky here. So the derivative becomes that because I have to lower that. The 2 multiplies the negative a half and becomes negative 1x. There's the derivative. It's actually a lot easier than the actual formula. So that's the formula to find the slope of the tangent for any value of x for that, instead of going through the x plus h thing. Okay, and you might say, what about this one? This one, before you solve it, you have to use the exponent rule. Because if you just start lowering the 4 here, it gets very confusing about what happens here. And we're going to get into something called the chain rule later on that'll let you solve this quicker. But right now, we must multiply these exponents to see what actually is happening, which is x to the 8. Now I can use the power rule. 8 comes down, multiplies the 5, and the exponent lowers by 1. That's the answer. Oh, I don't know if it's going to let me. Oh, I know what I have to do for this one. So this one, unfortunately, we don't have a proper rule. There's a faster rule to do it. We have to rewrite this, and they're saying for when t is equal to bigger than 0. Yeah, bigger than 0, I guess. So we're going to have to rewrite it. So we're going to keep that in brackets. And it's actually the same as multiplying. Well, that is 1/2. Yeah, I think we can keep the 2 down there. Yeah, let's bring it up. 2 times t. I don't think it's 2 times t. I think it's 2 to the negative 1 times. Yeah, I think we have to keep the, oh no. So it's multiplying. Yeah, I think I can do it like this. That's the same as that. And if I treat that all as 1, it's the same as this. Keep it all in brackets. Now, I think technically they're wrong. Because, yeah. Because I think I have to distribute before I can multiply these things. I think I have to. We'll try it out and see what happens. What the hell? So, before I can solve this, I must distribute it. So what's t to the 5 times 2 t to the negative 1? Yeah, this is where I think I'm wrong. I think I have to keep it. I think I have to keep the 2 like this. Okay, what's t to the 5, and essentially it's over 1, times t to the negative 1? Well, when you multiply two things with the same base, you add their fractions. So what's 5 plus minus 1? T to the 4, all over 2, because this 2 still sticks around. Then when I multiply the minus 3 times 2 to the t to the minus 1, rather, I get the 3 still. And when I add 2 plus minus 1, I get t to the 1, but all over 2. That makes it a lot easier. There we go. Okay, a little tricky there. I hope I'm being clear. So I don't have to write to the 1 here. Let's rewrite this so that you can see what coefficients are actually in front of these terms. There, that's a lot clearer, isn't it? Okay, now to find the derivative, now I can find the derivative. I bring the 4 down here. 4 times a half becomes 2, and then I have to lower the exponent by 1. This is a 1. It comes down. It's very easy to do the derivative of anything to the 1. It's that. There's the derivative of that using this very tricky. And the reason I didn't want to bring the 2 up, I believe it still would have worked, but I'd have this weird 2 minus 1 thing times 3, and it looks really weird like that. It's easier to leave the 2 down below and bring the t up. So that's the derivative of that. That one's probably pretty tough at this stage for most people. Okay, and they just get you to do it over and over again, which makes sense because unfortunately in maths, when you're teaching a bunch of people at once, the best method is to get the kids to do it over and over again, because you will remember things when you write them down. You will repeat them when you learn the rule from writing them down. And you will do well in the tests when you do many of these questions. So this is the big part that was learned a long time, is that most students remember things when you write them down. So if you're just sitting there staring at the book, solving these in your head, it is useless, because 2 days from now, you will forget it. And I'm going to have to emphasize that. So, let's, oh, am I not, oh, damn you. Okay. Let's just start with number 4. So they're getting you to do the same thing, but obviously it's going to get more and more complicated as you do it. Crop. But it's the same thing. Bring the fraction down. You'll see that these cancel out a bit. And lower this fraction by 1. This could also be rewritten as this. Same thing. Let's go to a more complicated one, like this one. Or actually, I'll just keep doing the simple ones. But if they're really simple, I'm just going to skip it. Minus 1 comes down here, minus half. Minus half times 4 becomes minus 2. And I get x, and then I'm going to lower this fraction by 1. So what's minus a half? Minus 1, minus 2 over 2. So it becomes minus 3 over 2. And that's the same as this, which is the same as this. Sorry. There we go. Notice the power went there, and the square root goes there. So these are easy if you rewrite them up top. That's the same as 6 times x to the minus 3 plus 2 times x to the minus 2. And I'm going to forget about this because the derivative of that is going to be 0. Bring the number down here. I get minus 18 times x to the minus 4. All I did was lower the exponent by 1. This one I get minus 4 when I bring this down and multiply by the 2. X to the minus 3. And if your book wants to, you can rewrite it like this. What did I do? I simply made this part go to the bottom. Don't bring the 4 with them, because the 4 does not have a negative exponent over it. The 4 is just a numerator multiplier coefficient. This is correct. This is not. Or wrong. The 18 never had a minus 4 over it, only the x that came from the bottom. This is no different, even though they try to make you think it is. Minus 2 comes down. Get minus 18. x to the minus 3. And this is the same as a half. So when you have a half come down, you end up with 3 over 2 times x to the minus a half. And if you want to rewrite this properly, the minus 18 is on its own. If it was in brackets, then yeah, the minus 18 would come down, but it's not. And you get x thirds down to the 3 down here, plus 3 over 2x square root of x. That's what this is. The 2 is already down there as a denominator, and the 3 stays up as the numerator. So that's the same as that. So again, what's the secret to this one? Convert all these powers to an exponent, or all these roots to an exponent. And then when you do this one, you get x to the third to the half. So you got to convert that to 3.5 as the exponent to that x. And then you just follow the same rule. And this doesn't matter. It's still a number. It's going to disappear. So this one's going to become half x to the minus a half. And then it's going to be plus 3 seconds times 6. And then that x is going to come down when I subtract 1 to a half. So what happens here? 3 times 3 is 9. You get 9 square root of x. And this becomes 1 over 2 times the square root of x. And a plus symbol in between. This one's interesting. This one you must distribute once you bring the x up. So this is the same as this. Put a bracket around this. This is the same as this. This is where confidence with your rules of math really apply. Now I can distribute it. What's x to the minus 1 times 1? And here's an interesting one. What's x to the minus 1 times this? So I got plus this. Let's just keep it separate. So I got a plus times a plus, right? So they're going to stay plus. And I got x to the half times x to the negative 1, which is negative 1 over 1. And the rule is you add them. So I have to add a half to a negative 1 over 1. And what's a negative 1 over 1 in halves? It's a negative 2 over 2. And I have to add them. Well, now I can now that the denominator is the same, it's just going to stay. And what's 1 plus minus 2? It's the same as 1 minus 2. 1 minus 2 is minus 1. So I get minus a half. So that means when these multiply out, when you add their exponents, that's the rule of exponents, you get x to the minus a half. Now this is the actual function still. We haven't taken the derivative yet. Now that we have it in this format, we follow the same rules. This becomes minus 1 times x to the minus 2. And this becomes, when this minus a half multiplies this plus 1, it becomes a minus half times x to the minus 3 over 2. That's what happens when I subtract 1 from this. Okay, rewritten, I get this. Minus 1 over x squared, that's what this is. Minus 1 over 2 times the square root of the cube power of x. That's what that is. There's your answer. Woo! Okay, again, this just is showing that when you take a derivative of something that's distance based on time, you're going to end up with velocity, because the slope of any triangle, I wish I could do a triangle, I'll do it like this, the slope of any thing where this measures time and this measures distance, when I take the slope I get distance over time, and that's velocity. It's easier when you see it like that, isn't it? So they're essentially asking you to take the derivative of this. Same rules. 2 comes down in front, you get minus 4 to the t plus 7. That's the derivative of that. This would help if you just rearrange it in its proper terms, in proper order. Okay, so I would rearrange it like this, just so that your answer makes more sense. You're allowed, this is called communicative property of math. When things are being added or subtracted, you can rearrange them. The same when things are only being multiplied or divided, you can rearrange them. Okay, 3 comes down in front. I get 3 times negative a third, becomes negative 1, t squared. This was always easy, it's always 5, and this is always easy, it's always nothing. Boom. A lot easier when I put it in the right order. This one, until we get to the chain rule, you have to expand it. You might as well get used to the expansion. The expansion is t squared minus 6t plus 9. Now I can take the derivative. The derivative for that is 2t. The derivative of that is 6 minus 6, and there's none for that. That is the derivative of that. And this, again, will produce a slope value for the tangent for any value of t for this. Essentially, will give you the instantaneous velocity for that, and so will all the other ones. Notice that they get you to do a lot of these over and over and over again. Determine the functions of this when a is 4, so they're asking for a specific point. So at first, let's solve it as a derivative so that we can figure out. This is essentially saying, you know, point A. So that's x is equal to 4. See? At any given value of a. I know they say a is equal to 4, but they're really saying when x is 4. They're just trying to keep your points and your equation separate so you don't get confused. So what's the derivative of that? What's the derivative of that? We'll keep the minus sign, and it's x to the half. So the half comes in front, so it becomes minus a half in front, and the x to the half gets lowered by 1, so it becomes minus a half. Now let's rewrite that. It becomes 3x squared minus 1 over 2 times the square root of x. Now, they gave us a specific value, that a is equal to 4, or x is equal to 4. So now we can plug it in. 4 squared, 16 times 3, 48. Minus 1 over 2 times the square root of 4. What's the square root of 4? 2 times 2. What's 2 times 2 down here? Minus 1 over 4. I'll save you some time. It's going to be 47 3/4. But if you want to put it into fractions, you'd multiply the 47 times 4 and then add it to the 3. I'm not going to do that because I can just say this is the same. 48 minus a quarter is the same as 47 plus 1. That's what 48 is. Minus a quarter. So when I take this part, I end up with 3/4. And I just keep my whole number down there. So the answer to that is the slope when x is 4 for this equation, the instantaneous slope, the slope of the tangent for that point is 47 3/4. See how much faster it is than doing x plus h minus x? Oh. Sorry. Just answer that. Hello? Yeah, prank phone call. Now, look how confusing they make this over here, right? Well, rearrange it. Rearrange it. First of all, let's put this over here. Get rid of it. And it's plus in the middle, plus 7. Because you see plus 7 in the beginning. And it's 5 2/3 minus. Okay, let's do the 2/3 first. 2/3 goes down in front. You get 2 times 5 over 3. which is 10/3. So it's just a fraction that's multiplying it, and 2/3 minus 1 becomes minus a third. I'm going to get used to that. This I'm going to rephrase as minus 6. And the nice thing about this, forget about it. It's just a number. Derivative of the number is 0. So minus 6 times x to the half. So when the half comes in front and multiplies minus 6, I end up with minus 3. And then the x, which was a half, when I subtract 1, becomes negative a half. Now I'm going to rewrite this. X in a third is 10 over 3. And down here is the cube root of x. That's all this negative means, and that's all this third means. Cube root, send it to the denominator. Minus 3 over square root of x. That's all this means. And the minus 3 stays up top. Okay, now they're asking us to solve for 64. Okay, so we're going to put it in the left side first. Just make a copy. When I put 64 in here, the cube root of that is, I believe, is it 4? 4 times 4, 16 times 4, 64. So I get 10 over 3 times 4, which is 10 over 12. Great. Minus 3 times the square root of 64, which is 8, minus 3 over 8. I can't subtract these. I could see right away that they actually have a common factor of 24. So if I multiply this left fraction by 2 over 2, I get 20 over 24. And if I multiply this other fraction minus by 3 over 3, I get 9 over 24. And that's because I could see that 8 and 12 are both factors of 24. Now that I have them both over 24, what's 20 minus 9? It's 11 over 24, which means the slope of the tangent when x is 64 for this equation is 11 over 24. It's way faster than doing x plus h minus x. Or sorry, f of x plus h minus f of x. And again, just assume that the slope of the tangent, you're going to need it, because that's what math is. It builds up on other things. Right? Determine the slope of the tangent curve, so they're doing it again. Okay? Again, and again, and again. And I would recommend, if you're really comfortable, stop doing problems, move to the next problem. But if you find you get tripped up by negative exponents, which you do, which everyone does, okay, so clearly they're looking for a specific value of x, and they're looking for the slope of the tangent. So we don't have to worry about the 3, because that only matters for f of x plus h. We only have to find the derivative of this, which is 12x cubed. You haven't figured out how I came up with that? Now, I don't need this y. That's just a red herring. I just need the 1, because that's the x value for this tangent. So what's 1 cubed? 1 times 12, 12. So the answer is the slope is 12 when x is 1. The slope of the tangent is 12 when x is 1 for this equation. I didn't even need the y. Okay, so keep that in mind when you do the rest of them. You might even be smarter to do this. Okay, how do I figure out this? Well, they're getting tricky here, because x to the 9 minus 5 at the bottom says send x to the other part of the fraction. That's just x to the 5. So they're just being jerks with this one. Why would you write that like that? And remember, that's when x is equal to minus 1. So this is very clearly an easy derivative to take. And then when x was minus 1, when you get a 4 power, any even power, it'll become positive 1 times 5. So the slope of this function at the slope of the tangent of this function at x is equal to minus 1 is 5 plus 5. Okay, so forget about the y value, and we'll just put this aside. Let's rewrite this. It's the same as 2 times x to the minus 1. Bring the power down. You get minus 2 x to the minus 2. What does that mean in mathese? It means minus 2 over the square root of x. All right. Right away, you might say, we got a problem. I can't plug in minus 2 over here, even though the point exists. Because I know that over here, when minus 2 is plugged in this equation, I get a point like that. So, the question is, how do we solve it? Does it have a tangent? And why not? Let's look at Desmos. Desmos is great visually, so we're doing y is equal to 2 over x. So f of x is equal to 2 over x. And we're going to see why. We're going to put in the point, what was the point? Minus 2 comma f of minus 2. And that should have a tangent. There's definitely a tangent there. So did I make an arithmetic error? Maybe. Let's take d over dx of f of x, and we're going to make hx equal to it, and we're just going to solve h of minus 2. So I got clearly an arithmetic error somewhere, because there is indeed a tangent there, and it's sloping down at 0.5. So what did I do wrong? Let's go back and look. Oh, I know what I did wrong. It's minus 2 to the x to the minus 2. That's not square root of x. That's minus 2x squared. My bad. That's just a brain fart. Okay. And you can see how easy you can trip up. So now when I substitute minus 2 into the equation, I get minus 2 over positive 4, which is minus a half, which is the same as Desmos told me, negative 0.5. That is the slope of the tangent for here. By the way, the thing I just did, this is really handy right here. This is Leibowitz's notation. It's saying make h of x equal to the derivative of f of x up here, d over d of x times of f of x. And then you can just plug in any value for h that you want to find. Great way to verify your answers in your homework if you don't want to keep flipping back. It's also a great way to study your graphs and understand what you're doing. So use your tools. You know, when I was young, there was no computers. You had to walk 2 hours just to get the answer. Okay, and it's the same thing over and over again here. And so I'm going to walk through it faster and faster as we go. And what are we looking at here? Which one did we just do? We did that one, right? So let's do this one. So how do we solve the... Oh, no, we did that one. They were being jerks on that one. Okay. And this one. We didn't solve this one. There we go. D. That's what we're trying to solve. Make it bigger. No problem. Okay. So we've got to put this in a fraction format that we an exponent format that we understand. It's the same as, in brackets, 16x cubed to the square, which means I can square root this and I can square root that. So that becomes 4x. And how do I do this? I multiply the exponents. That's all it is. Look at that. Much easier in this format, isn't it? And if the trick is here, you can easily see that 16 has a square root. So it's really this, which is what we solved. So x, 4 times x to the power of 3 over 2. You bring the 3 over 2 in front, and you get 6. And then when I subtract from that, I get a half. So that means 6 square root of x is the formula for the slope of the tangent. When I put 4 in here, square root of 4 is 2. 2 times 6 is 12. So the slope of the tangent for x is equal to 4 for this function is 12. frustrated after you do a bunch of these. So again, the formula should be, if you can do it, move on. So determine the slope of the tangent to the graph of each function at the point with a given x. So I'm going to race through them, and if it's something tricky, I'll stop. So the derivative of this, f prime of x, is 6x squared plus 3. So when x is 1, I get 6 plus 3. It's 9. Great. Moving on. What about this one? I have to convert all my x values to an exponent. And the nice thing about this is when I take the derivative, this is just going to go. Half goes in front. Subtract 1 up here. I get 1 over the square root of x. So when x is 4, I get 1 over 2. And that's the slope of the tangent for this function at x is equal to 4. Okay. Obviously, I have to put it in a format that I can understand it. So this is the same as 16 times x to the minus 2 minus 32 x to the minus 3, which is the same as minus 32 over x cubed. So when I do x cubed, notice that a minus 2, when it's cubed, stays a minus 8, and minus 32 divided by minus 8 is plus 4. So the slope of the tangent, in this case, at this x for this function is plus 4. And the last one, you have to expand it first. Later on, there's a faster way. So what's this? You have to add their fractions, their exponents. And then what's this? X to the minus 3. So that's the expansion of that. How do you solve the derivative? Here it is. Okay, how do I rewrite that? Great. Now I just got to put 1 in there. They've made my life easy with 1. So I end up with minus 4 minus 3 minus 7. So the slope of the tangent at this point for this function is minus 7. Write an equation of the tangent each curve at these points. Didn't we just do this? That's just very similar. Woo. Over and over and over again. So this one I'm just going to do a couple. It's the same rules, and I'll do the toughest one. What's the toughest one in here? This looks pretty hard. This is just an expansion, so I'll walk through what you do. This, you have to put x up top as a negative, and then you solve each one individually. Once you solve it in, even though they've given a weird notation here, this is the only thing that matters. This does not. Once you solve the derivative here, you punch this in and get a solution. That is not that hard. We've just done 1,000 of them. This, you've got to bring the x's up top. Okay? So and just give yourself some room. Forget all about this 7. You only care about the point x of minus 1. And this is going to be the same as this. At which stage, solve them individually. Okay, the minus 2 comes in front. The minus 3 comes in front, and lower the exponents. And then once you have a formula for derivative, punch in minus 1. Not that hard. This one, you have to convert it to a fraction, an exponent that makes sense. And remember to keep, because the 3 is in here, you have to keep it in there like this. Okay. Oh, sorry, that is not the correct thing. And now guess what? You can, let's see, 3 times 3 is 27. Yeah. You can individualize this if you want. So you can rewrite this if you like, but I believe that you can just leave it there. Let's see if I get the same answer. So I'm saying that you can put that 3 as a cube root of 3 square rooted times x to the 3 halves. And let's see if that makes a difference. Let's do it 2 ways. So I'm going to bring the 3 half in front. 3, and I get 9 halves times x to the half. Oh, sorry, 9 halves times x to the half. Okay, which is the same as square root of x. And so we're saying for the position, Jesus, what position were they asking about? They were asking for position, so not 3. X is equal to 3. X is equal to 3. Interesting. Yeah, I got it right, at least this part. So you're going to get 9 times square root of 3 over 2. And that's the only answer. Let's see if I get the same answer over here. And I can see already it's already a mess. And the reason I say this square thing must be applied to 3 before I can multiply it is because this 3 is not really a 3. So I don't think this answer is correct. This 3 is actually a cube of 3, which is 27, square rooted, which doesn't have a square root. So it's really like saying this. And I believe this is actually correct. So now I bring the 3 over 2 in front, and this becomes a half. And so it's actually 3 over 2 times the square root of 27x, because you're allowed to multiply square roots. Now let's see if that makes more sense. And so when x is 3 in here, I get 3 times, yeah, that makes more sense. This is actually harder to do, and I'll explain that again in a second. So when it's 3 here, 3 times 27 is 81, so 3 times the square root of 81 divided by 2, which is 3 times 9 divided by 2, which is 27 divided by 2. You see, I did not get that answer over here at all. And now let's explain why. Let's see if it'll let me, yeah, it will. You have to remember, they kind of were mean to you here, that the 3 is in the square root. And actually, no, I've made a mistake already, because the cube does not apply to it. So I made a mistake on the cube. So this answer is wrong. Sorry. But the square root does apply to it. So if I'm going to rewrite that as a fraction, it's like this. And to solve that, I have to apply the square root to the 3. I accidentally applied the 3 over into the 3. And to solve the x, I have to multiply that. There we go. That is correct. This is the correct rewrite of that. My bad. Now you can take the derivative of it. And the derivative of it says I take the exponent, put it in front, and lower the exponent by 1. And this is the same as 3 halves times square root of 3 times square root of x, which is the same as the square root of 3x. Now I can punch in 3, and I get 3 times 2 times the square root of 9, which is 3, and I get 9 over 2, not 27 over 2. That's the correct answer. 4.5 is the slope of the tangent for this point for this function. Yeah. See, these are tricky. Okay, how about these? Okay. This one you have to expand it. So when I multiply this out, I get x squared over x, so I just get x. And when I multiply this one out, I get plus 1 over x squared. To find the derivative of that, I have to rewrite it as x to the minus 2. Now I can take the derivatives. The derivative of this is just 1. And the derivative of this is minus 2 x to the negative 3, which is minus 2 over x to the 3. There's the derivative formula. For 1, I get 1 minus 2, which is minus 1. There's the slope of the tangent. That was actually a lot easier than it looked. The last one was a lot harder. This one here, don't know why I jumped here. This one here is a lot easier than it looks. Or maybe it's not, who knows. And the secret is you have to expand it first. So you do square root times square root of x, you get 3x. Square root of x times 8 plus 8 square root of x. Minus 2 times 3, essentially, minus 6, and then there's the square root of x. And then minus 2 times plus 8, minus 16. Right away, I know the derivative of a number is going to be 0, so I can get rid of that. All I have to do now, and I know the derivative of that is going to be 3, but let's just rewrite it for now. I have to rewrite this as a fraction, and you can see now it's quite easy to solve. X to the half. The halves go in front. I get 3x. Well, the derivative of that is 3. This I get 4 over square root of x. And this I get minus 3 over square root of x. I've skipped a couple steps, but it's the same thing. Now when I plug in 4 here, I get 4 divided by 3 plus 4 divided by 2 minus 3 divided by 2. So I might as well solve this. What's plus 4 over 2 minus 3 over 2? 1 over 2. 3 plus 1 over 2, 3.5. That's the slope. And the last one. You have to take the top, put it in brackets, and multiply it by the bottom, which is the same as, what is the bottom rewritten here? It's x to the third. Bring it to the top, it's x to the minus third. That's how you move things up and down. Now I have to distribute it. So to do that, I have to put this as a fraction of x. What happens when I multiply the same base? I add their exponents. What's a half plus minus a third? The same as a half minus a third. That's the same as 3 over 6 minus 2 over 6. So I get 1 over 6. So I get x 1 over 6 minus 2x to the minus 1/3. Okay, how do I take the derivative of this? It's 1/6x. And when I subtract 1 here, I'm left with minus 5/6x. Minus 2, take this down, times minus a third becomes plus 2/3. And when I subtract 1 up here, I'm left with minus 4/3. How to rewrite this properly? Okay, let's start with this one. How to rewrite this properly? This negative sends the whole thing down to the bottom. So get 1 over 6 x to the 5/6. Now you can leave it like that. Your calculator can solve exponents like this. Plus 2 over 3 times x to the positive 4/3. But if I'm going to rewrite it in square root format, I get 6, and I'm going to take the 6th root of x, and I'm going to take the power of 5 of it. That's what these are. And then I'm going to add 2 over 3 times the 3rd root of x to the power of 4. Now they've given me a nice softball number. 1, this is just all going to become 1. So get 1/6 plus 2/3, which is 1/6 plus 4/6, which is 5/6. You can come out with a decimal if you want. Take this number, divide by that, come up with a decimal. And that's the answer. Woo! They made that one really complicated. How many more of these do I have? Oh, God, I don't think I can do. It's going to have to be part 1 because I just don't have the time right now to go through all of these. This is a similar thing to what we were doing in the last question. It's just you use the tricks. But I'll do them. And then, of course, when we get into part C down here, we're getting into So this is part 1, 2.2. It's the best I could do at this time.